Welcome back. In this session, we will talk about the cloud design patterns that will help us with various aspects of microservice communication. A messaging based architecture at some point must be able to send, receive, and manipulate large messages. Such messages may contain anything including images, sound files, text documents, or any kind of binary or data of arbitrary size. Sending such large messages to the message bus directly is not recommended because they require more resources and bandwidth to be consumed. Large messages can also slow down the entire solution because messaging platforms are usually fine tuned to handle huge quantities of small messages. Also, most messaging platforms have limits on message size, so you may need to work around these limits for large messages. So, how do we solve this issue? The answer is claim check pattern. Store the entire message payload into an external service, such as a database. Get the reference to the stored payload and send just that reference to the message bus. The reference acts like a claim check used to retrieve a piece of luggage, hence the name of the pattern. Clients interested in processing that specific message can use the obtained reference to retrieve the payload if needed. Consider the following points when deciding how to implement this pattern. Consider deleting the message data after consuming it if you don't need to archive the messages. Although the blob storage is relatively cheap, it costs some money in the long run, especially if there is a lot of data. Deleting the message can be done synchronously by the application that receives and processes the message, or asynchronously by a separate dedicated process. The asynchronous approach removes the old data with no impact on the throughput and the message processing performance of the receiving application. Storing and retrieving the message causes some additional overhead and latency. You may want to implement logic in the sending application to use this pattern only when the message size exceeds the data limit of the message bus. The pattern would be skipped for smaller messages. This approach would result in a conditional claim check pattern. Moving on, the number of requests can vary significantly over time for many reasons. A sudden increase in user activity or aggregated requests coming from multiple tenants can cause an unpredictable workload. At peak hours, a system might need to process many hundreds of requests per second, while at other times the number could be very small. Additionally, the nature of the work performed to handle these requests might be highly variable. Using a single instance of the consumer service can cause that instance to become flooded with requests, or the messaging system might be overloaded by an influx of messages coming from the application. To handle this fluctuating workload, the system can run multiple instances of the consumer service. However, these consumers must be coordinated to ensure that each message is only delivered to a single consumer. The answer is competing consumer pattern. Use a message queue to implement the communication channel between the application and the instances of the consumer service. The application posts requests in the form of messages to the queue, and the consumer service instances receive messages from the queue and process them. This approach enables the same pool of consumer service instances to handle messages from any instance of the application. Consider the following points when deciding how to implement this pattern. Message ordering. The order in which consumer service instances receive messages isn't guaranteed and doesn't necessarily reflect the order in which the messages were created. Design the system to ensure that message processing is idempotent because this will help to eliminate any dependency on the order in which messages are handled. Detecting poison messages. A malformed message or a task that require access to resources that aren't available can cause a service instance to fail. The system should prevent such messages being returned to the queue and instead capture and store the details of these messages elsewhere so that they can be analyzed if necessary. Handling results. The service instance handling a message is fully decoupled from the application logic that generates the message, and they might not be able to communicate directly. If the service instance generates result that must be passed back to the application logic, this information must be stored in a location that's accessible to both. In order to prevent the application logic from retrieving the incomplete data, the system must indicate when processing is complete. Scaling the messaging system. In large-scale solution, a single message queue could be overwhelmed by the number of messages and become a bottleneck in the system. In this situation, consider, consider partitioning the messaging system to send messages from a specific producer to a particular queue, or use load balancing to distribute messages across multiple message queues. Ensuring reliability of the messaging system. A reliable messaging system is needed to guarantee that after the application enqueues a message, it won't be lost. This is essential for ensuring that all messages are delivered at least once. Moving on. In many cases, the order requests are received in by a service isn't important. In some cases, though, it's necessary to prioritize specific requests. These requests should be processed earlier than lower priority requests that were sent previously by the application. The answer is priority queue pattern. A queue is usually first in first out structure, and consumers typically receive messages in the same order that they were posted to the queue. However, some message queues support priority messaging. The application posting a message can assign a priority to the priority, and the messages in the queue are automatically reordered so that those with a higher priority will be received before those with a lower priority. In systems that don't support priority-based message queues, an alternate solution is to maintain a separate queue for each priority. The application is responsible for posting messages to the appropriate queue. Each queue can have a separate pool of consumers. High priority queues can have a larger pool of consumers running on faster hardware than lower priority queues. Consider the following points when deciding how to implement this pattern. Define the priorities in the context of the solution. For example, higher priority could mean that messages should be processed within 10 seconds. Identify the requirements for handling high priority items and other resources that should be allocated to meet this criteria. Decide if all high priority items must be processed before any lower priority items. If the messages are being processed by a single pool of consumers, you have to provide a mechanism that can preempt and suspend a task that's handling a low priority message if a higher priority message becomes available. Using a separate queue for each message priority works best for systems that have a small number of well-defined priorities. Message priorities can be determined logically by the system. For example, rather than having explicit high and low priority message, they could be assigned as a high fee paying customer or a non fee paying customer. Depending on your business model, your system can allocate more resources to processing messages from fee paying customer than non fee paying ones. There might be a financial and processing cost associated with checking a queue for message. Some commercial messaging systems charge a small fees each time a message is posted or retrieved, and each time a queue is queried for messages. This cost increases when checking multiple queues. Moving on, an application performs tasks that include a number of steps, some of which might invoke remote services or access remote resources. The individual steps might be independent of each other, but they are orchestrated by the application logic that implements the task. If the application detects a more permanent fault it can't easily recover from, it must be able to restore the system to a consistent state and ensure integrity of the entire operation. The answer is scheduler agent supervisor pattern. The pattern defines the following actors. These actors orchestrate the steps to be performed as part of the overall task. The scheduler arranges for the steps that make up the task to be executed and orchestrates their operation. These steps can be combined into a pipeline or workflow. The scheduler is responsible for ensuring that the steps in the workflow are performed in the right order. As each step is performed, the scheduler records the state of the workflow, such as step not yet started, step running, or step completed. The state information should also include an upper limit of the time allocated for the step to finish, called the complete by time. The scheduler maintains information about the progress of the task and the state of each step in a durable data store called the state store. If a step requires access to a remote service or resource, the scheduler invokes the appropriate agent, passing it the details of the work to be performed. The scheduler typically communicates with an agent using an asynchronous request response messaging. This can be implemented using queues. The agent contains logic that encapsulates a call to a remote service or access to a remote resource referenced by a step in a task. Each agent typically wraps calls to a single service or resource, implementing the appropriate error handling and retry logic. If the steps in the workflow being run by scheduler use several services and resources across different steps, each step might reference a different agent. This is an implementation detail of the pattern. The supervisor monitors the status of the steps in the task being performed by the scheduler. It runs periodically, the frequency will be system specific, and examines the status of the steps mentioned by the scheduler. If it detects any that have if it detects any steps that have timed out or failed, it arranges for the appropriate agent to recover the step or execute the appropriate remedial action. Note that the recovery or remedial actions are implemented by the scheduler and agents. The supervisor should simply request that these actions be performed. You should consider the following points when deciding how to implement this pattern. This pattern can be difficult to implement and requires thorough testing of each possible failure mode of the system. The recovery retry logic implemented by the scheduler is complex and dependent on state information held in the state store. It might also be necessary to record the information required to implement a compensating transaction in a durable data store. How often the supervisor runs will be important. It should run often enough to prevent any failed steps from blocking an application for an extended period, but it shouldn't run so often that it becomes an overhead. The steps performed by an agent could be run more than once. The logic that implements these steps should be idempotent. So, what did we learn? We learned about the claim check pattern to handle large messages. We learned about competing consumer pattern to handle multiple consumers. We learned about priority queue pattern to handle important messages. We learned about scheduler agent supervisor pattern to coordinate distributed actions. Thank you for listening. Please get back to us in case of any questions or comments.